Okay, now let's go ahead and calculate our unit normal vector based on, well, by calculating the perpendicular component of our acceleration vector. This continues the example when we had r of t equal to cosine t I plus sine t j plus I believe it was t over pi quantity squared k. Yeah, that's right. Okay. Now we took our derivative of this to get what we can interpret as a velocity vector or our r prime vector, and we took the derivative of that and we regard that as acceleration or r double prime vector, and we find the perpendicular component of that vector by doing what? Doing a minus the parallel component of a. Okay? Now the parallel component of a is easy enough to calculate, okay? And I didn't go through the details of calculating it. Here's my a vector. You can see that this follows from this. Take two derivatives of this, you get this. My a parallel vector obtained by projecting the a vector on the unit tangent vector, and you can go back a couple of videos and see how that was obtained, is just this, and you can verify that calculation. There's the projection, the parallel component of the a vector. When we subtract these two vectors, you can verify that this is what we get. The I component is going to be negative cosine t, and then it's going to be minus a negative this times sine t. So here we have this, here we have our sine t, there's our I component. We do the same with the j and the k components. And I think I've got those right. Yeah, okay, I was looking at this. It looked like I'd factored that out. I was looking at it wrong. Okay, so I believe that that's probably our perpendicular vector. Okay, now, I didn't take class time to do all the mess of writing out and simplifying what you would get if you divided this vector by its magnitude. Okay? You know, it's pretty big, messy, but there's some simplification. It's still pretty messy. But that gives us our normal vector. You can write that out. It's just a matter of writing it out and making sure you do it carefully and include everything and don't include anything twice, and do a reasonable job of simplifying it. Otherwise, it's much harder to work with. So that's how we get our normal. Now again, we're talking about this function which gave us the non-uniformly stretched helix. Now we want to calculate the binormal vector that I talked about. Well, I'm not going to write out the calculation. You should write out the calculation. Okay, but the calculation is very simple in principle. You just take the cross product of the unit tangent vector, which isn't all that bad, with the normal vector, which is somewhat worse, this one. The vector you get when you write this thing out and then divide by the square root of all those squares. Okay, the sum of all those squares. In any case, that gives you your binormal vector. So if you have a point on this helix, you have a unit tangent vector in the direction of motion. You have a unit normal vector perpendicular to the unit tangent vector. So there's your unit tangent vector and your unit normal vector, and you cross those two vectors and you get your binormal vector, this thing. And as discussed, with respect to just the x and y motion, the motion always points, or the unit normal vector always points back toward the center because you're moving around a circle, and the vector perpendicular to the tangent vector in a circle is the radial vector. Okay, now the normal points inward toward the center, not outward as the radial vector would, but it's still parallel to the radial vector. Okay, so that if you're just moving in the circle, even if you're speeding up or slowing down, the normal stays perpendicular to the tangent vector, and you have kind of this type of motion. Okay, if this is your tangent vector, this is your normal vector. So you're moving around the circle, looks like this. It looks like I've been gesturing off camera. I thought I was kind of there, but maybe I was too close to the camera. Okay, the B vector, and that almost looks like a B prime, but that's just a flaw in the blackboard, is perpendicular to this. Now, if you're going up along the helix, well, then your motion is getting increasingly steep. So your unit tangent vector is no longer in the xy plane or parallel to it. It's going to be like this, and your unit normal vector is going to follow along. Okay, and your binormal vector follows along. So as you get steeper and steeper, your motion kind of looks like this. Also, the unit normal now has a k component that you can see in evidence here. Okay, and these two vectors are going to start out in the plane, but then they're going to tip upward like this. And what's that do to your binormal vector? Well, it kind of tips it outward like this. Okay, then you ask yourself, what's it feel like to be riding along that helix? I'm not going to talk about that right now. We need to kind of digest this. Briefly, you're going to feel yourself tilting with respect to gravity if you're riding this helix and it's vertical. If the z-axis is vertical, and you're going to feel an acceleration that's not just toward the center but also somewhat upward. It's going to be kind of a weird feeling. So don't want to talk too much about that right now. This is how you calculate it.